forgot to do this. Okay, STP. Well, that stands for standard temperature and pressure. Okay, standard temperature and pressure. Now, here's standard temperature and pressure. That is 0 degrees Celsius, and then the pressure is 1 atmosphere pressure. We are approximately right now 1 atmosphere pressure, and that varies depending on what part of the country and how high you are from sea level, but approximately we're at 1 atmosphere pressure. Okay, so only at 1 atmosphere pressure and only at 0 degrees Celsius, this is true, that 1 mole of gas will occupy a volume of 22.4 liters. Okay, that's important, but only at 0 degrees and 1 atmosphere. If a word problem does not state either STP or 0 degrees 1 atmosphere, then this is not true. Okay, only in those conditions. That 1 mole of any gas, be it hydrogen, fluorine, ammonia, xenon, methane, has a constant volume of 22.4 liters. Okay, now they all have a different molar mass, obviously. Hydrogen 2.2 grams per mole, fluorine 38, and etc. 1 mole, they all have the same number of molecules. Avogadro's number 6.02 times 10 to the 23rd. Okay, and obviously 1 mole of all these gases, we all got 1 mole here. Okay, the only differ is the molar mass, simply because it's a heavier elements involved for each gas, but they all share the same volume, 22.4 liters per mole, which is another ratio, keep in mind, that we can utilize to do calculations with liters in the numerator or moles in the numerator. Okay. All right, so let's clear that. So we call that molar volume. Okay. Again, at molar volume, 1 mole of any gas at STP occupies a volume of 22.4 liters. Now, how can we use that? Okay. Well, here's the question here. What is the volume of 1.25 moles argon gas at STP? Okay. Key part, STP. Without that, we can't do anything. The answer would be cannot calculate. Not enough information given. But here we're at STP. And so we write down what we're given, 1.25 moles of argon gas. We're at STP, then we can use that relationship with liters in the numerator and moles in the denominator. Again, setting up the problem so that moles cancel out, leaving us with what we're looking for. So about 1.25 moles of argon gas, 1.25 moles of argon gas, we'll have a volume of 28 liters. Okay, 28 liters. Now, here's something to check when you look at the problem. What if you inadvertently reversed it and you had moles on top and 22.4 liters in the bottom when you did the math? Well, you're going to have a very small volume. But that's not consistent with the fact that you're given it over 1 mole of gas. So you should have a number greater than 22.4 liters. And in this setup, it's correct, 28 liters. So that answer makes sense. Okay. So sometimes we're quick to set it up and just plug in the numbers in the calculator and then just report that number. Well, look at that number. Does that number make sense? Does that make sense based on the mathematics that we did? All right. Next question. How many moles is 30.4 liters of oxygen gas at STP? Okay. And so look at the problem you're given. It's 30.4 liters, which is a lot greater than 22.4 liters. So I can probably make an educated guess here and say, you know, my answer should be greater than 1 mole, because I know that in 1 mole there's 22.4 liters. I'm being given 30.4 liters. And so if I set that problem up with moles in the numerator, liters in the denominator, liters cancel out. Okay. And my answer is 1.36 moles. Again, consistent with the liters that I'm given, which is greater than 22.4. Okay. Now here, the last number 3, they're asking the question, okay, if I have 4.5 liters of chlorine gas at STP, how much does it weigh? What is the mass? Okay. So I may need a couple of conversion factors here. One, I need to convert the liters to moles, okay? And then 2, once I know the moles of fluorine gas, by the molar mass of fluorine, I have the mass, the grams. And so I need 2 conversion factors here, okay? The first one, because we're in STP, converts the chlorine gas to moles of chlorine gas. My liters are canceled out because I set that up properly. And then I need the molar mass of chlorine, but remember, chlorine gas is diatomic. And so I need, what I think is 35.45 times 2. So the molar mass for chlorine gas is 70.9 grams per mole. And setting that problem up, my moles cancel out, leaving me behind with grams with respect to units. Okay. And so now I plug in the calculator, 4.5 divided by 2.4 and times 70.90. I'm left with 14.2 grams with the correct number of sig figs. Okay. Now, the I lost my train of thought here for a second. With respect to sig figs, remember the atomic weights, we don't use those to determine sig figs, but the 22.4 is a measurement, okay? And so it could play a factor with respect to significant figures in your answer. Now, it has 3 sig figs there, but our problem gives us 4.50, it has 3 sig figs. So, our answers should end up with 3 significant figures. But if that 4.500 was given, then that's 4 sig figs, and therefore our answer would be defined by the 22.4 with respect to sig figs. Okay. So the 22.4 is a measurement. So it would play a factor in your significant figures. Now, so the main thing to take away from this, for gases only at STP 0 degrees, 1 atmosphere, that relationship is a true relationship that you can utilize. And so we have this flow chart here that kind of helps you go through units, depending on what you want to go through. Notice something. To get from any point, from grams to molecules or from grams to volume, you can only do it through moles. Okay. Moles is the common factor that all these calculations have. If I want to get to from grams of A to grams of B in the reaction, I can't go directly grams to grams. I need to convert everything to moles. Once I'm in the moles, from that point, I can go to any direction that I need. So our common source, our common factor is moles. So if I'm given grams, okay, and I need to get to volume, I need the molar mass, okay, to get me to the moles, which then, using the 22.4 liters per mole, gets me to the volume. Okay. If I need to figure out how many atoms, I need the molar mass to give me moles, and then I need Avogadro's number to get me 2 atoms. Okay. Now I can go from atoms to volume, but to do that, I need to go through moles. So I can go in any direction here, from grams to atoms, from grams to volume, back and forth, but I gotta get through moles. Okay. All right. An example. Okay. How many grams does 17.35 liters of neon gas mass at STP? Okay. So you have 17.35 liters of neon gas. They're asking you how much does it weigh? What is the mass if you're at STP? Then they're asking you, all right, well, how many atoms does this correspond to? Okay. And so I need to write down what I got, what I'm given, 7.35 liters. I went ahead and gave you the answer there. To 15.6 grams, this should be your final answer. But I need my conversion factors. First conversion factor, since I'm at STP, gets me to moles of neon gas. Then my second conversion factor is the atomic weight of neon gas that you get from the periodic table, which is 20.18 grams per mole. Okay. I double check and make sure that I set this up properly. Okay. By looking at my units, liters cancel out, moles cancel out. I'm left with units of grams. Okay. And notice here, I'm given 17.35 liters, 4 sig figs. Earlier I said that 22.4 liters is a measurement, and it may be a factor in your sig figs. And in this case, yes, it is. Okay, because it's 3 sig figs for 22.4. So our answer should have no more than 3 sig figs, which is 15.6 grams. So if you were in the lab and you were able, and you wanted to, for whatever reason, you needed 15.6 grams of neon gas, that's a hard thing to go out and weigh. But we can measure volume in the lab. We have ways to output a certain volume. But if you're at STP, you can fix it so the volume that you output would weigh 15.6 grams. Okay. All right. So now then they ask you, well, how many atoms does this consist? How many atoms is 17.35 liters? All right. So set up the same thing. We write down what we're given. I got to get to moles. So I still use the 22.4 liter per mole relationship. Okay. Then I bring in Avogadro's number, which would tell me how many atoms of neon gas I have. Okay. And before I do anything, any of the math, I double check to make sure that my units all along cancel out properly when I do the math. Moles cancel, liters cancel. Okay. Leaving me with atoms, which is what the question asks for. So 17.35 liters of neon gas at 0 degrees and at 1 atmosphere has a mass of 15.6 grams, and there are 4.66 times 10 to the 23rd atoms of neon. Okay. Which brings us to density. Okay. Actually, we can, density deals with another ratio. We had talked about this a while back, which is mass per volume. Okay. But we can utilize molar mass divided by molar volume if we're at STP. So for example, here they ask you to calculate the density of ammonia gas at STP. Well, we need the molar mass. Okay, molar mass of nitrogen is what, 17? Yeah, 17.04 grams per mole. And we divide that by the molar volume, which at STP is 22.4 liters per mole. Doing that, our units cancel, leaving us with grams per liter, which are the units of density. Okay. All right, so we can use molar mass and molar volume to calculate density of gases at STP. All right, which brings us to this chapter, a few more slides and we're done with this chapter. The percent composition. Okay, in calculating the molar mass of any compound, we've done this already for the number of things. We simply add up the atomic weights of all the atoms in the molecule to determine the molar mass. Okay. Well, we can take it one more step. If we take, and the percent composition is no different than like your percent grade. I mean, there's a percentage in your grade that comes from the quizzes, a percentage comes from the homework, percentage comes from the activities. Okay, this is basically what it is. Here you have a total, you have a total amount, the whole, and you're taking the part of each, like I say, the part that every element contributes to the molecule and dividing it by the whole. All right, so let's take the example of water. We know there's two waters, okay? We know that the molar mass of water is 18.0 grams, 18.02 grams, 2 hydrogens, 1 oxygen. Every hydrogen brings in 2.02 grams, okay, because there's two. And if we divide that by the molar mass of water and multiply that by 100, guess what? We get a percentage of 11.2% hydrogen, okay? We do the same for oxygen. So that's 16 divided by 18.02. Multiply that by 100, we get 88.79% oxygen. So in a molecule of water, there is 11.2% hydrogen and 88.79% oxygen. Okay, that percentage should add up to be 100 if you did the math properly, and if you counted the elements, the number of elements properly, you should add up to 100%. And this water, be it water we get here or water we get out in space, it's H2O. It will have the same composition. We do this in the real life chemistry, where in the lab, when I was making new compounds, I would take a sample and send that out for analysis. I would send it out to ask how much carbon I have in it, how much hydrogen, how much nitrogen, how much oxygen, any other element that I thought would be in there. And then the percentage will come back and we can back calculate and actually come up with a formula for the compounds that we made. And then coupled with other instrumentation, we can actually get a good, a correct structure. Okay. So that's the percent composition, nothing complicated. All right. So let's find out the percent composition of TNT. You might be familiar with this. This is a good old fashioned dynamite. It stands for trinitrotoluene. And anybody by chance know who discovered TNT? No. Well, there's a prize that's given every year for science and medicine and literature and peace. It's called the Nobel Prize. Alfred Nobel was the one who actually synthesized TNT, and that was a game changer for him because that became very important for a lot of industry, and unfortunately also became used a lot in the military. But TNT, trinitrotoluene, they're asking you to calculate the percent composition. It's okay, you don't know the structure of this, that's not what we're looking for, but you're given the formula there. You're given 7 hydrogens, 7 carbons, 5 hydrogens, 3 nitrogens, and how many oxygens do we have here? How many total oxygens do we have? Anybody want to take a educated guess? Actually, you don't have to guess. It's right there. Here you go. Exactly. 6. Okay. And so we set the problem up. We first have to calculate the molar mass for this molecule. And the molar mass ends up to be 227.15 grams per mole. Okay. And then we go individually. Carbon brought in 84.07 grams, hydrogen brought in 5.05 grams, nitrogen brought in 42.0 grams, and oxygen brought in 96.00 grams. Divide each one of those by the molar mass times 100, and TNT consists of 37.01% carbon, 2.22% hydrogen, 18.5% nitrogen, and 42.26% oxygen. Okay, and that is a percent composition of trinitrotoluene, otherwise known as dynamite. Okay, try these at home, work these out. Here's the answer for you. The first one says, how many liters will 3.425 grams of carbon dioxide occupy at STP? If you set that problem up, you should end up with 1.74 liters. Okay. Second question asks, how many molecules are in 3.425 grams of carbon dioxide? So you're given the amount of carbon dioxide. Okay. You need to calculate the molar mass of carbon dioxide, which means you're going to need the formula, right? And once the molar mass is determined, you know how many moles of carbon dioxide you have, and then you utilize Avogadro's number to give you the number of molecules. And you should come up with 4.68 times 10 to the 22 molecules of carbon dioxide. And then the last one, how many grams will 3.0 times 10 to the 15 molecules of carbon dioxide mass? Okay, if you had a way to measure 3.02 times 10 to the 15 molecules, how much does it weigh? Okay, that's what they're asking. Okay, so try these at home. Your answer should be 2.2 times 10 to the negative 7 grams. Okay, which brings us to the end of chapter 12. So, any questions about this one? No. Okay. Which brings us to chapter 13. Big old fancy word here, stoichiometry. But you already are familiar with it. You probably don't know it. Okay. All right. So if I had I always use the bicycle examples a lot. Let's say I had a bicycle frame, a two-wheel bicycle frame. So obviously it requires 2 tires, correct? So 1 frame and 2 tires. And so the stoichiometry of the bicycle frame and the tires is 2 to 1. The ratio is 2 to 1. Remember when we were balancing the chemical equations in the chemical reaction chapter? I mentioned at that point, okay, once you balance it, look at that coefficient. Remember this, you're going to need this later on. And that's the relationship between reactants. Okay. If I had a tricycle frame, 3 tires, I need 3 tires. So the stoichiometric relationship between the tricycle frame and tires would be 3 to 1. And if I had a unicycle, it's 1 to 1, 1 tire per 1 frame. Okay. Your car, the stoichiometric relationship between your car and your tires is a 4 to 1. I need 4 tires in that car. Okay. And this is what it's all about. And it's related to balancing the chemical equations, because that stoichiometric relationship, that ratio, like any ratio we've been talking about, can be set up one or two ways. And how we set that up depends on the question. Okay. All right. Well, let's look at this. We went here. We got nitrogen monoxide reacting with oxygen to give us nitrogen dioxide. And so we balanced it. So we got two NOs with one oxygen gives us two molecules of nitrogen dioxide. Okay. If we were to use 10 molecules of NO, that means that I need 5 molecules of oxygen. And that means that I'm going to make 10 molecules of nitrogen dioxide. Now we could replace the term molecules and just say moles. Okay. So we say here that 2 moles of nitrogen monoxide and 1 mole of oxygen will give us 2 moles of nitrogen dioxide. And so the relationship between NO and oxygen is 2 to 1. The relationship between NO and nitrogen dioxide is 2 to 2, or 1 to 1. The relationship between oxygen and the product, nitrogen dioxide, is 1 to 2. Okay. That is a stoichiometry of this chemical reaction. Okay. And so if I had 10 grams of nitrogen monoxide and I needed to calculate how many grams of nitrogen dioxide, well, I need to first convert the grams of NO to moles. And once I know the moles of oxygen of NO, given the balanced chemical equation and that stoichiometric relationship, I now know the moles of NO2 because it's a 2 to 2 or 1 to 1. Okay, that's how we use stoichiometry to calculate calculations. And this stoichiometric relationship is true whether I do it in the lab in small scale or I have a big industrial plant that's making tons of this material. It's the same stoichiometric relationship. Okay. All right. Next example here, we got N2 nitrogen reacting with hydrogen gas to give us ammonia. Once we balance the equation, we have 1 nitrogen, 3 in front of the hydrogen, and 2 for the product, ammonia. And so we use a similar wording that one molecule or 1 mole of nitrogen requires 3 moles of hydrogen gas to give us 2 moles of ammonia, the product. Okay. So the stoichiometric relationship between the reactants is a 1 to 3. 1 nitrogen for 3 hydrogens, or 3 hydrogens for 1 nitrogen. Whichever way you look at it, it's the same thing. The relationship between nitrogen and ammonia is a 1 to 2. And note the relationship between hydrogen and ammonia is a 3 to 2. Okay. 3 to 2 relationship. All right. So anytime we balance this reaction, we make sure we recognize the stoichiometric relationship, because now we're going to have a question to ask us. For example, it could say, if I have, and let's assume we have, oh, hold on. Come on, where are you at? Let's assume, just for argument's sake, I got 10 grams. We're at STP. STP. Okay. Question will be, well, how many grams of ammonia can I make? Right? That might be the question. And so I need to look at the stoichiometric relationship between these two, which is a 1 to 2. and I need to know that information. Okay, I have 10 grams of nitrogen, STP. Okay, I can convert that to moles, of, because I'm at STP, but I need the molar mass of nitrogen. Once I know the molar mass, you know, we can figure out how many grams of ammonia. We're going to do examples like this here in a bit. Okay, so coefficients gives us the mole ratios. Let's take a look at this reaction here. Okay, we have iron 3 oxide reacting with carbon monoxide to give us iron and carbon dioxide. Okay, after we balance the equation, we see that we need 1 mole of iron 3 oxide, and we need 3 moles of carbon monoxide, which will give us 2 moles of iron and 3 moles of carbon dioxide. So if we look at the reactants first, okay, if I look between here and here, I see it's a 1-to-3 relationship, okay, because based on the balanced chemical equation. That means that I can write that relationship either like this with iron 3 oxide in the numerator or carbon monoxide in the numerator. Okay, it's a ratio. I can write it one or two forms, just like a conversion factors that we did way back when. Which one I use depends on the question, but keep this in mind. Just like the conversion factors, whatever units I need at the end always ends up in the numerator. Okay. Now, some may be tempted to change the 3. Don't change the 3, just leave it like it is. You might want to take a third of that and put a number in there. My suggestion, just leave the coefficients like they are. Just take them, write them like I just wrote them up here on the slide. Okay. Changing that coefficient, changing that 3 to a third kind of messes things up a little bit. You're better off just to keep the coefficients on there. And then if we look at the other relationship between carbon monoxide and oxygen, which is between here and here, okay, that relationship we can set up as so. 2 irons per 3 carbon monoxides, or invert that, 3 carbon monoxides to 2 irons. And so you have the relationship. Let me clear this for a minute to point out all of the relationships that you have. Okay, and so between reactants you have. Let me clear that again. Okay. Okay, between reactants, you have this relationship between the iron and the carbon monoxide, 1-to-3. So that's one relationship. And then you have the relationship between the iron 3 oxide and the iron. It's a second relationship. And then the third relationship between the iron oxide and the carbon dioxide. Okay. So you got 3 relationships just with iron 3 oxide. And each one, you can write that relationship 1 or 2 ways. Now, the other relationship, let me get a different color, is between carbon monoxide and iron, and carbon monoxide and carbon dioxide. Okay, so there's 2 relationships there on top of the 3 already. Then you actually have one more, and that's the relationship between iron and carbon dioxide. Okay, and all of those are ratios that you can utilize to do any type of calculations. Okay, and that is true for any reaction. There's a relationship between the reactants, and one of the reactants and the products, the other reactant and the products, and then between the products themselves. All right, so the first question asked here is how many moles of iron can be formed from 2.2 moles of carbon monoxide? All right, so we're looking between iron and carbon monoxide right here. We're not concerned with anything else. The problem is asking between carbon monoxide and iron. Okay, and so we can see that the relationship is a 3 to 2. And so we can write it as so. And so if we start off with 10.2 moles of carbon monoxide, then from the balanced chemical equation, the stoichiometric relationship is 2 iron per 3 carbon monoxides. That means that it would form 6.8 moles of iron. Note how the units cancel out. Moles of carbon monoxide cancel out. Moles of carbon monoxide cancel out, leaving us with moles of iron. Okay. All right. Next question is how many moles of iron 3 oxide are needed to form 17 moles of carbon dioxide? And so we're looking at the relationship between iron 3 oxide and carbon dioxide, which is a 1 to 3. We're not concerned about any of the other reactants or the products, only between the iron 3 oxide and the carbon dioxide. And so we can write down what we're given, 17 moles of carbon dioxide. And then from the balanced chemical equation, since we're looking for iron 3 oxide, that's in the numerator, and carbon dioxide cancels out. Moles of carbon dioxide cancel out, okay, leaving us with moles of iron 3 oxide. And so that requires 5.7 moles of iron 3 oxide. Note here, we're stopping at moles, but we can go to grams from that answer. Okay, we can go 5.7 moles of iron 3 oxide to grams of iron 3 oxide by calculating the molar mass of iron 3 oxide and setting up with grams in the numerator, moles in the denominator, and that will actually tell us how many grams we need. Okay, but right now we're stopping at moles, but the obvious next step is to go to grams. Why? Because when you're in the lab, you're not measuring moles of anything. You're measuring grams. And so you got to take the grams, convert to moles, and then from moles, convert that to grams. Okay. All right. Right, let's balance this equation. We got sulfur dioxide and oxygen. Okay. All right, so we look at this and we say, all right, sulfurs look okay. We're balanced. Oxygens, we have a total of 4 on the left-hand side, reactants, and 3 on the right-hand side. So we can do this any couple of ways, but if I put a 2 in front of sulfur trioxide, okay, that gives me 6 oxygens. And so I got to put a 2 now in front of sulfur dioxide to balance my sulfurs. And guess what? The oxygens balance out. I now have 4 oxygens from sulfur dioxide, 2 from oxygen, and they're balanced. The stoichiometric relationship between sulfur dioxide and oxygen is a 2 to 1. Between oxygen and sulfur trioxide, it's a 1 to 2. Between sulfur dioxide and sulfur trioxide, it's a 1 to 1, or because it's 2 to 2, which is a 1 to 1. Okay. Note the relationships there. You got this relationship here, then we got this relationship here, and then we got this relationship here. Okay. All right. So the question is, how many moles of sulfur trioxide, figure that out, will form if 0.165 moles of oxygen reacted? And so all we're concerned about is between oxygen and sulfur trioxide. And that's a 1-to-2 ratio there. All right. And so we set up the problem. Write down what we're given, 0.165 moles of oxygen. From the balanced chemical equation, we're looking for sulfur trioxide. So that is in the numerator. So that's a 2/1 oxygen. Okay. And so you can see that it is twice the amount, will form twice the amount of oxygen, because it's a 2-to-1. So we just simply multiply 0.165 times 2. All right. Now the next problem is, how many moles of sulfur dioxide are needed to make 0.04 moles? So we need to calculate, I need to make 0.04 moles of, let me get an arrow. I gotta go from here to here. Okay, so I need to make 0.042 moles sulfur trioxide. How much sulfur dioxide do I need to use? Okay, and this is a typical type of problem you actually find in industry. Right now we're just making a small amount of 0.042, but if, let's say, for example, you need to make a ton of this, well, you will use the same calculation to make a ton of this. Obviously, you would need different equipment. That's where the chemical engineer comes into play. The chemist would develop the general reaction, and then the chemical engineer would figure out how to transport a ton of material from point A to point B. Okay. All right. So that's where we got to go. So we write down what we need, what we're given, 0.042 moles of sulfur trioxide, and it's a 2-to-2 relationship, or a 1-to-1. So that means that I need the same amount of sulfur dioxide to begin with in moles. Keep in mind, we're still at the moles, but the next obvious step would be to calculate grams. All right. So this is another flow chart to help you out, related to the flow chart we had before. All right. Notice what is being done here. We are trying, if we're given grams of something, some compound, and we're looking for grams of whatever compound we're looking for, we need to get through moles. Okay. And so here I got grams of A. How many grams of B am I going to make? Okay. So I cannot go directly from here to here. Cannot do that. I have to go through moles. Okay. And so what they're telling you here is that the information that I need, sorry about that, let me clear this up, is the molar mass. I need the molar mass of what I'm given. Okay. From the balanced chemical equation, the mole ratio, the stoichiometry, I can find the moles that I'm looking for. And once I know the moles that I'm looking for, what I'm trying to find, if I determine the molar mass of the compound I'm looking for, I calculate the number of grams. Okay. So to go from A to B in grams, I need the molar mass, I need the balanced chemical equation, stoichiometry of the two, the reactant and the product, and the molar mass of the product, and I calculate how many moles I can make. Okay, let's try an example. Okay, here we have this reaction here. Can anybody tell me the name of this FeO? If I had to name that, how would I name that? Anybody want to take a shot at it? FeO. I gave you the name of Fe2O3, where I called it iron 3 oxide. What would be the name of this guy? FeO. You can unmute yourself or you can type it in. I'm trying. Iron. Well, we know it's iron. Fe is iron. Talking about this one here. Let me change the color. What is the name of this guy? FeO. Iron 2 oxide. That's correct, Abigail. Remember oxygen? The ion of oxygen is a -2 oxide. So that means that iron must be a +2. Therefore, if we had to name it, it would be iron, parentheses, Roman numeral 2 oxide. Good. The other one was Fe2O3. And that meant that that iron must be an iron 3. Okay. All right. So here we have 2 iron 2 oxides reacting with 2 aluminums to give us 3 irons and aluminum oxide, AlO2, aluminum oxide. You might find a lot of that, those you do your fingernails or your, what's that, what do you call that thing, that bar to smooth out your fingers? It's a lot of oxide material. File, what am I saying? You know, that file. It's aluminum oxide. So that's the chemical reaction. Questions is, has it's even balanced for you. Make note of the relationships, 2 to 3 for reactants, 3 to 3 from iron 2 oxide to iron, 3 to 1 from iron 2 oxide to aluminum oxide, 2 to 3 from aluminum to iron, and 2 to 1 from aluminum to aluminum oxide. Okay. So the first question is calculate the mass of iron 2 oxide needed to react completely with aluminum. So right now, you're given 5.55 grams of aluminum and you need to figure out, well, how much iron 2 oxide do I need to completely react with it? Okay, so the only thing we're concerned about here in the first question are the reactants. That's it. We don't care about the products. They're just talking about the reactants. So we note the relationship. It's a 3 to 2 relationship between iron 2 oxide and aluminum. Okay. The second question is calculate the mass of aluminum oxide produced if 10.25 grams of aluminum reacted completely. So in here, we're looking at how much aluminum we need to make 10.25 excuse me, the other way around. How much aluminum oxide are we going to make? How much aluminum oxide we're going to make if we start off with 10.25 grams of aluminum. The first one was calculate the amount of aluminum oxide needed to react. That guy needed to react with aluminum. Okay. So that was the red part. All right. All right. Well, let's what time do I have? Oh, I tell you what. All right. I think I'm gonna stop it here. It's chapter 13. I will stop it here and I'll continue with it tomorrow. And the next chapters 14 and 15, they're not so big, they're not too big either. So we're probably gonna be ahead of schedule as far as finishing this up.